So here we are. Looks kind of weird. So what are we getting here? It doesn't really look like it's blowing up. In fact, it looks like it's imploding. Look at that. Kind of a cool effect anyway, but certainly not what we were going for. What's happening is that by default, a lot of force stuff in Houdini is considered an attractor. See how the arrows are pointing towards the metaballs in this picture? So that's exactly what's happening. It's getting a strong attraction force, which is working. And of course, the whole thing is collapsing because there's no glue anymore. But, we want it to explode. So we're going to have to change that. And let's first disable the simulation here by clicking on the brain down here. So now I can click and go around without worrying about losing the cache. I mostly just want to make sure I have this cache for this next part. So we disable the sim. We go to the metaball force. Just negate the force here. Now it will blow out the other direction. So we can be fairly confident that that will work. Also, we might as well turn these back on. In any case, once we run the sim again, let's do a thing here now so that we can disable the glue ourselves. So once again, here it is. Now we know that it's moving now, even if it is doing the wrong thing, and we don't see it moving in here. That's because Houdini doesn't actually update where the constraints are over the course of the sim. It will show you in the 3D viewport, if you visualize it, at runtime, it will transform them into position. But in fact, under the hood, as we are literally here in the SopSolver, we are extracting the relationship constraints here. So we need, even if we don't end up doing anything with our visualization that we're going to make here, I like to visualize where the constraints are on a given frame. I want them to be updated into the positions they would be based on the pieces that they have constrained together. It's just pretty easy to do. We basically just need to bring in the simulation into here where the pieces are, and then because we know these constraints have the names of the pieces that they correspond to, we can just look up where those pieces are and update these points to those positions. So let's do that. So we'll say call this get pieces. And then we want to target the simulation, which is ... because ... would be the SopSolver, and ... is the thing above that, which is the sim. Now we're not asking for everything in the sim conceivably, which is what this would be. I want to specifically say, just get me the dynamics object that was called RBD something, because I forget again, and get me the geometry data from that. So now we can be sure that we won't get a whole bunch of stuff that we didn't actually want. To see it here again, if we were out in this is the sim, that's the ... and then colon is, these are the dynamics objects that are being placed into our sim. Again, they're not the nodes themselves. This node is not a dynamics object. It creates the object from the node and puts it into the sim. So that's why we use a colon, because it refers to something that's not a node. It's referring to some kind of, ghost container in the sim. And the sim itself, and the dynamics object itself, has this geometry data, and this is that kind of SOP stuff that we're used to working with. So that's why over here, get pieces is the sim colon the rigid body, or really in this case, all the rigid body objects that are being made, which is just the one, and then geometry. And before we even continue, also remember, this is creating an RBD packed object. So that's what I'm talking about when I'm talking about objects. I'm not talking about the individual pieces on here. I've been calling those pieces. The object is this dynamics object. Like the ground plane makes an object also, which also has an object name. And that's why we see this here. We see this here. And in the case of the RBD packed object, it's this packed geometry inside that acts as the individual pieces. Alrighty. So the SopSolver, we now have two things. We've got the constraints, which know the names of the things they constrain, and now we have the simulation, which, as you can see, if I scrub, there it is. So what we want to do is update these points to these positions. So I'm going to say, let's make a point wrangle starting from there, and we're going to reference this in some manner by asking for input 1. This is input 0, 1, 2, and 3. Because of computer science, of course, we start on 0. So here we go. I'll say update positions. And we're going to use a really cool, one of my favorite Vex functions actually, which is, we'll say int point is find attribute val. That's find attribute value. It's really cool. Normally, a lot of the functions we've been using have been saying, hey, get me the attribute at this point or at this primitive. What this will say is, get me the pointer primitive that has this value. So it's kind of a reverse lookup. So in this case, from input 1, which is where the dynamics pieces are coming in, from input 1, there is a point attribute called name, and look up my name and return to me the point number where you find it. So let's say that again. In input 1, which is the piece is coming in that input, there is a point attribute, which is true. Remember, the point attributes are these, and there is a name. There's an attribute called name. That's a point attribute. That's what this is saying, and this is saying. And so we're looking up. What are we looking up? You can pass any value in here. I could type a string here. In this case, though, because we're iterating on the constraints, and the constraints also have this name thing here, this at name is referring to the current name value on the point that we're iterating on in the constraints here. So we're looking up the name in this thing and saying, what point has that? And now we have it. Now that's stored in this integer point here. So now that we have it, we can ask this stream for anything based on this point number. So I can say, all right, well, I know what point number has the thing. Now we want the position, of course. That's the whole reason why we're here. So I'm going to update my position at P based on the position in input 1 at, of course, the point we just looked up. And that's it. So now, when I do this, oops, that's a plus sign. There you go. Now you can see the constraints are moving with the sim. Huzzah. So if we wanted to do any number of things, for example, these constraints now have changed length. You know, some are longer than they are, some might be shorter. You could measure the constraints and say, oh, you're too long now, break it. Or you're too short, make it stronger or something. I mean, I don't know. You could do whatever you wanted. You could say maybe if this constraint enters this area, break it. But now that we effectively know where how the constraint is represented based on where the points are, you can do a lot with that. And if nothing else, it's a good visualization for debugging later on.